relationship with them. Then topic as well, you are going to learn the diagram that are related to various processes and learn on how to draw the diagram as well as how to read the diagram. Basically, in thermodynamics, one or the fundamental of thermodynamics, they have three types of diagram. First one is pressure versus volume, or PV diagram, and temperature versus volume, or PV diagram. Last but not least is the P diagram, the 3D diagram. But on this level, for your level, we just focus more on P diagram, the first two, pressure versus volume and temperature versus volume. Forgot to record this discussion. Let me record for this week first. Suara saya slow. Okay, let me increase my voice, the volume of my voice. Okay, next, we will look at the phase changing process for pure substances. This one, look at how the pure substances change their phase from one form to another form. Then last one, you are going to learn how to read the property table of thermodynamics. Because in this property table, they have too many data as well as properties. So from this table, we can get the data and solve too many problems. So I hope you can focus more on this chapter, because this is the first step before we go details on thermodynamics. If you can't understand chapter number 2, face a problem on next chapter, because chapter number 2 is the first step for you to learn thermodynamics. Okay, before we go further, let's look at the meaning of pure substance. In chemistry, we always define a pure substance as an element or a compound, a substance that something cannot be separated. This is what we call as a pure substance. But in thermodynamics, we define pure substance as something that has a fixed chemical composition throughout. Okay, for example, here we have several pure substances: nitrogen, air. This nitrogen and air can be formed of vapor or liquid. Water and air also are the example of pure substance. So as you know, in nature there have three phases of matter: solid, then water, liquid, and last one is gas. So in terms of solid, the molecules are kept at their positions by the large spring, like intermolecular forces, as shown in my slide. Okay, this is example of solid. So the molecules stay in their position. They can be vibrate at their position, but molecules can be moved, from one position to another position. So that's why the molecules are kept constant at their own position, but it vibrates. The solid, the attractive and repulsive forces between the molecules tend to maintain them at relatively constant distances from each other. The meaning for a solid. Then, as we learn in high school, the temperature is increased, then the solid can be changed another form of matter. Example, liquid, then if more heat is given to this liquid, then substance change to another form, gas. Okay. This is the definition for each phases: solid, liquid, and gas. For solid, the pattern is in three-dimensional. It has large attractive forces between their atoms or their molecules. And then the atom or molecule itself are in constant motion, but they still vibrate. Okay. If the molecule has enough energy, then it can the, the bonding between the molecules can be broken. Okay. The phase will change to another phase, which is liquid. So when a solid reach a high enough temperature, vibrations are strong enough, chunks of the solid break off and move past each other. Okay. For the gas, their molecules are far apart, no long or short range order, and they have high enough kinetic energy. So in order to liquefy this gas, lots of energy, lots of the kinetic energy must be released from the molecules of gas. Want to change gas back to liquid, then we have to release the kinetic energy of the atom or the molecules. Okay, now let's look how the phase change happened. Okay, the pure substance phase change from one phase to another phase. So here we have a piston cylinder system. The substance inside this piston cylinder device is liquid water. So at the beginning of this process, the pressure is 1 atm. The temperature is 20 degrees C. Okay, the pure substance is in water. So meaning that the phase is 100% liquid. So now let's consider what happens when we give heat to this pure substance or water at constant pressure. At constant pressure means that we keep the pressure of the device of the system at 1 atm. Okay. So now let's look what will happen one by one. Okay. So for the first phase, I mean for the first state of this process, the temperature of our pure substance is 20 degrees C. Okay, so now the phenomena of this phase changing process can be shown or illustrated in terms of TV diagram. So we will use TV diagram in order to understand or imagine how the pure substance occur. For example, now during state number 1, the temperature is 20 degrees C, and the volume or specific volume of our pure substance is very low, okay, as shown in my figure. My figure here, the temperature is 20 degrees C and has a low value of specific volume, because the piston now is at a low position. So if we plot in our TV diagram, our first state or state number 1 is located at here. Okay, since the temperature is very low, 20 degrees C, and our specific volume is here. I mean around here at a very low value of specific volume. Okay, now heat is given to our pure substance continuously, while the pressure is kept constant at 1 atm. Okay, then since heat is given continuously given to our pure substance, the temperature increase from 20 degrees C to 100 degrees C. Pressure is kept constant at 1 atm. Okay, during this condition, the volume is slightly increased. The volume of the system is slightly increased because some of the liquid here is transformed into it's not transformed yet, but the molecule of the liquid start to move randomly, because the molecules or atoms of the liquid obtain energy from this heat. So that's why the volume or specific volume of the system is slightly increased to another position. So now our state 2 become this because the temperature is increased from 20 degrees C to 100 degrees C here, and then the specific volume also slightly increased from V1 to V2 around here. Okay, around here. So this is how the process from state number 1 to state number 2. Okay, then heat is still given to liquid, but now the temperature is remain constant. Because from state number 2 to state number 3, the boiling process start to be occurred. Okay, some of the liquid here change to vapor. Okay, to vapor here. That's why the specific volume of this system increased drastically. So the vapor, the molecule or atom of the vapor push the piston upward. Okay. So at this condition, the temperature is 100 degrees C, constant as state number 2, because boiling process is started. Okay, started. So if we draw in terms of PV diagram, since the temperature is constant for state number 2 and state number 3, the position of number 3 is still same on the same level with state number 2, because they both of them have same temperature. But now number 3, state number 3, the specific volume is drastically increased. So we have to plot number 3 on the right side of state number 2. So somewhere here, okay, where V3 must be larger than V2. Okay, V2 is around here, somewhere here, and V3 is somewhere here, and it must be larger than V2, specific volume number 2. Okay, then heat is still continuously given, okay, from state number 1 until state number 4. So during state number 4, the temperature is still constant, because during this condition, most of the all of this liquid form change to vapor. 100% means that during state number 4, the substance is totally in term of vapor phase. So meaning that during state number 4, the boiling process is over, is completed. That's why the temperature here is 100%. Okay? And the specific volume also increased, because the gas push the piston more, and the piston the piston change from position during state number 3 to another position upper than state number 3. So if we draw a TV diagram, the point the point for state number 4 is on the right side, where the volume, specific volume 4, still is larger than V3 here. Okay, this 4 is here. That now the piston has big value of specific volume. Okay. And then finally, after the boiling process completed, if heat is still given, the temperature now will start to increase drastically. Okay. After the boiling process, heat is continuously given to our pure substance, the temperature of this vapor will start increase drastically to 300 degrees C. Okay, so that's why if we plot state number 5, the position of number 5 is upper than position number 4, because the temperature for state number 5 is higher than temperature of state number 4, where at state number 4 the temperature is 100 degrees C, but now the temperature for state number 5 is 100 degrees C. And of course, the specific volume keep moving or keep increase to another level, which is a V5 here. Okay, so basically this is how the pure substance change their phases from initial phase to final phase. As we know, water, if we give heat to our water, the water will the phase of our water will change from one phase to another phase, from liquid, then from totally liquid at temperature, and it will change to vapor or gas. given continuously. Okay, this is how the process occurs, or the pure substance process, the pure substance phase process occur. Okay, so far, if you have any question, then you can ask me before we look to our next slide. Okay, so ini adalah proses asas bagaimana sebuah substance bahan berubah fasa, change its phase from one phase to another phase. Okay, again, during state number one, phase of our pure substance is 100% liquid. At state number two, the phase is in 100% liquid as well, okay, but it tends to change its process phase, but not change yet, but tend to change. And during state number three, our pure substance has two phases, liquid and vapor. So they are coexist equilibriumly. So both vapor and liquid coexist equilibriumly during state number three. For state number four, all of the pure substance change to vapor. So here 100% is in vapor phase. No more liquid. State number four here. And during state number four, the boiling process is completed. For state number two, the boiling process start to occur. Okay, so the boiling process start during state number two, and state number four, the boiling process is over. If we give more heat after boiling process, then our pure substance change from a vapor here to superheated gas. Why superheated gas? Because the temperature is extremely high, 100 degrees C. Okay, and from this phenomena, okay, can draw a TV diagram in order to know what happened to the properties. Okay, so for example here, this is our TV diagram. T temperature versus V here is, if you look properly, this is small v, which is a specific volume. Okay, this is not volume but specific volume. Specific volume means that the unit is kilojoule per meter cube per kilogram. Meter cube per kilogram. That is specific volume. So now this is TV diagram. If we draw based on this phenomena, then we will get as this. The process start at here where the temperature is at a low temperature and low specific volume, same as this picture. Okay, the specific volume is very low, okay, because the piston is at the lower position or bottom position here. So that's why specific volume 1 is low, and the temperature is 20 degrees C. Okay, after heat is given, then the piston start to move upward slightly. So V1 change to V2, and the temperature increase from 20 degrees C to 100 degrees C. So now here, this is the position for state number 2, and the boiling process is started here. more heat, then boiling process occur. If not, then it will back to state number 1. So for this case, heat is continuously given and the piston move more upward since our pure substance has two phases. Some of them is in and another form is in vapor form. So now the specific volume increased from V2 to V3 and the temperature is constant. As I said just now, if we give heat, then the boiling process started. Since the boiling process started, the temperature is kept constant at 100 degrees C. Okay. Then heat is still given to our pure substance. So the specific volume change from V3 here to V4 because of all of the pure substance now is in vapor form. So vapor form, in order to have vapor form 100%, completely 100%, so they must have enough space for this vapor. So in order to have enough space for vapor, the piston must be pushed more upward, okay, to occupy the vapor. So that's why the specific volume 4 is higher or larger than V3. But the temperature is still constant because at this state, the boiling process over. Okay, over means that the temperature is 100 degrees C for water. Okay. So if we give more heat for state number 4, the temperature will start to increase drastically because boiling process is over and heat is given, so temperature become 300 degrees C. And of course, specific volume is higher than state number 4. Piston keep moving upward to occupy more of the vapor because the molecule of the vapor here now is has a very high kinetic energy. So the molecules and atom move extremely. So therefore, the volume here must be higher than state number 4. So that's why V5 is higher than V4. And of course, temperature is higher than 4. V4 is 100. Okay, next, for each process that we discussed in before this, as we discussed in the previous slide, they have their own name. For each phase, they have their own name. Okay? For example, here, the first one is compressed liquid. So compressed liquid means that a substance that is not about to vaporize. So if we look back to our TV diagram here, okay, during state number 1, the name of the phase is compressed liquid. It's not going to vaporize because the temperature is 20 degrees. It's not going to vaporize yet. So state number 1, the name of the phase is compressed liquid or subcooled liquid. Okay, number 2, saturated liquid. It is a liquid that is about to vaporize. A start boiling process is going to happen. Okay, so for during this condition, this time, the name of the phase is saturated liquid. So number 2 here, the phase name is saturated liquid, meaning that 100% is in liquid, and it starts to vaporize if heat is given, still given. Okay, if heat is still given, then it will vaporize. So at point number 2, state number 2 here, the name of the process is saturated liquid. Number 3 is saturated liquid vapor mixture. So from this sentence, I hope you can imagine the meaning, can guess the meaning. So during this condition, both liquid and vapor coexist equilibriumly. So they have two phases, liquid and vapor, at which the liquid and vapor phases coexist in equilibrium. This is the name for state number 3. So at this point, the name of the phase is saturated liquid vapor mixture. One. Number 4 is saturated vapor. Meaning of saturated vapor is a vapor that is about to condense. Condense here means that kondensasi lah. So meaning that if you release the heat, then it will condense. Not, then it will move to higher level of temperature. Okay, so number 4 is saturated vapor, a vapor that is about to condense. So number 4 here, state number 4 is saturated vapor. That 100% is in vapor. As I explained just now, during state 4, 100% of this pure substance is in vapor phase. That's why we name it as saturated vapor. Wak tepu. Okay, then last one is superheated vapor, a vapor that is not about to condense. Okay, so during state number 5, this is superheated vapor, a vapor that is not going to condense. Okay, so here to release heat during state number 5, this vapor is not going back to number 4. It cannot return back to number 4 or number 3. Keep in superheated vapor selama-lamanya. Okay, it's not going to return back to number 4. But during state number 4, if you release the heat, it will back to state number 3 and state number 2. Okay, this is the meaning of superheated vapor, a vapor that is not about to condense. Okay, this is how our 3D diagrams look like after we name the phases. Okay, so as we know, we have 5 states: state number 1, state number 2, state number 3, state number 4, and state number 5. So any point located between state number 1 and state number 2, okay, any point, any position between state number 1 and state number 2 on this line, the phase is called compressed liquid. So any point located on this line between state 1 and state 2, their phase is compressed liquid. And then between state number 2 and state number 4, the phase is saturated mixture. So meaning that any point located on this line between state number 2 and state number 4 is in saturated mixture. Okay, as I said in the previous slide, state number 3 is saturated mixture, right? Saturated liquid vapor mixture. So 3 can be here or even here. or even near to number 4. So all of this point, the name of the phase is saturated mixture. And then between point number 4 and point number 5, the phase name is superheated vapor. Okay. This is the last one, number 5. And point number 2, the name of the phase is saturated liquid. So you have to remember, number 2 is saturated liquid, and number 4 is saturated vapor. So now we have four names of phases. The first one is compressed liquid between number 1 and number 2. Number 2 itself is saturated liquid. In 2 and 4, it is saturated mixture. Number 4 itself is saturated vapor. And last one, between 4 and 5, it is superheated vapor. Okay, the pressure is 1 atm. So along this line, their pressure, the pressure of the phases is 1 atm. Okay, this is same as what we discussed in the slide. Okay, so in this slide, we see that the pressure is kept constant, right? So 1 atm, 1 atm here, also 1 atm, 1 atm, and state number 5, the pressure is still 1 atm. So therefore, along this line, the pressure of the phases, phase number 1, 2, 3, 4, and 5, their pressure is 1 atm. So this line named as a pressure constant line because the pressure is constant along this line. Okay, it's shown in my TV diagram here. This is TV diagram for the heating process of water at constant pressure. So pressure is 1 atm. Okay. Do you have any questions so far before we go for the next slide? You can ask me if you are confused on the TV diagram or the process, the pure substance phase changing process. So you can ask me before we go for the next slide. Okay, if not, then we continue to the next slide, the saturation temperature and saturation pressure. As we know, water boils at 100 degrees C and 1 atm. This is a condition, natural condition for water boiling process. But now in thermodynamics, 100 degrees C is called saturation temperature, not as what we known before. 100 degrees C is boiling temperature. Boiling temperature is a common word used in our daily life. Okay, boiling temperature itself is a common word that we use in our daily life. But in thermodynamics, name the boiling temperature as saturation temperature. Okay, so please remember this word. So during our course thermodynamics, we are not going to use or to say boiling temperature, but saturation temperature. The temperature at which a pure substance changes phase at a given pressure. For example, just now our our pressure is 180 m. So at a given pressure 180 m, the saturation temperature is 100 degrees C. Okay. In other words, okay, in other case, or in the second case, they have another word which is saturation pressure, Psat. So Psat or saturation pressure is the pressure at which a pure substance change phase at a given temperature. For example, other case, if the temperature at 100 degrees C boils our water. So we will have 180 m where the boiling process occurs. So for the first case, we keep the pressure constant, and then we will get the saturation temperature. Then for the second case, we keep the temperature at a constant value, and then we will get the value of saturation pressure. This is the difference between saturation temperature and saturation pressure. Okay, next. Now we have a PT diagram, and this diagram, PT graph or PT diagram, and this PT diagram show to us that the liquid vapor saturation curve of a pure substance. The higher the temperature, the higher the pressure. Okay? So the higher the temperature, the higher the pressure will be. For example, or in other words, the higher the pressure, okay, the higher the pressure, the higher the temperature will be. Or in other words, the higher the temperature, the higher the pressure will be. Okay, for example, if you are at the top of some mountain, okay, if you are now at the top of, for example, Mount Kinabalu, okay, so at that time you are going to boil your water, okay. So at that position, at the top of Mount Kinabalu, the pressure is higher or lower, high or low, at the top of Mount Kinabalu. We have learned last week in chapter number 1, the lower the position, the higher the pressure will be, right? The lower the direction, the lower the position, the higher the pressure will be. So the higher the pressure, the higher the position, the lower the pressure will be. So at the top of Mount Kinabalu, the pressure is low compared to the ground level or sea level. Okay. So if you want to boil a water at the top of Mount Kinabalu, where the pressure is low, the temperature for boiling process is low compared to level. So if you boil water on the sea level, you need 100 degree C, right? Since the pressure is 180 m. But at the top of Mount Kinabalu, since the pressure is very low, okay, compared to sea level, so somewhere here, so you just need a temperature which is lower than 100 degrees C. Okay, paham? The lower the pressure, the lower the temperature is needed to boil your water. The higher the pressure, the higher the temperature is needed to boil the pure substance. Water, what else? Your another liquid, okay? Your teh tarik, for example. Okay, faham? I hope you can understand the meaning of this PT diagram. This liquid vapor saturation curve of a pure substance, as well as this table 3.1. Okay, so the higher the pressure, the higher the temperature is needed to boil any pure substance. The lower the pressure, the lower the temperature for boiling process, or the lower the saturation temperature. Okay, next. Okay, now we will look at the diagrams. Here we have three types of diagrams: thermodynamic, and each diagram will tell us how the pure substance face a changing process occur. We have PV diagram and PT diagram. PV means that temperature versus specific volume. Second is pressure versus specific volume. And last one is pressure versus temperature. Okay, for this course, we will focus on PV and PV diagram. So let's look at the first one, temperature versus specific volume, P versus V diagram. This PV diagram is actually same as what we discussed in our previous slide just now. Okay, in the previous slide, we discussed the phase change at constant pressure 1 atm. So 1 atm means that 1 atm is this one 0.1 megapascal. 1 atm is equal to 101.32 kilopascal. So this is what we discussed just now. Okay, at 1 atm, this is the line that we discussed in our previous slide. But in this slide, it tells us that we can draw many lines based on the pressure. Okay? For example, we can draw 0.01 megapascal, but the line is lower than our 1 atm line here. And then we can have another value of pressure, for example, 1 megapascal, 8 megapascal, 15 megapascal, until 25 megapascal. Okay, so each pressure constant lines here will tell us the same meaning. Same meaning here means that, as we discussed in our previous slide, this point is saturated liquid. This point is saturated vapor. And around here, it is saturated superheated vapor. So between on this straight line, on this horizontal line, the phase name is saturated liquid vapor mixture, right? As this is what we have discussed in the previous slide. If we have 1 megapascal line, it will tell us the same thing. This is a saturated vapor. Here is superheated vapor. This is saturated liquid. And this line is compressed liquid line. This horizontal line is saturated liquid vapor mixture. Okay. For this PV diagram, since we have various value of pressure, this pressure tells us that the higher the pressure, okay, the higher the pressure, the higher the boiling temperature or saturation temperature, right? We have discussed here, the higher the pressure, the higher the saturation temperature will be. Okay? This is the concept, the theory. The higher the pressure, the higher the saturation temperature. The higher the saturation temperature, the higher the saturation pressure will be. Okay. So if we look at our TV diagram here, okay, the higher the pressure from 0.01 megapascal until 25 megapascal, the higher the saturation temperature. So as we learned just now, on this straight line, on this horizontal line, the pressure is constant. In other words, this is the saturation pressure or boiling saturation temperature, sorry, or boiling temperature. Okay, so during 0.1 megapascal, the boiling temperature here, as we know, it is 100 degrees C. The saturation temperature is 100 degrees C. So from the previous slide, from the previous theory, the higher the pressure, the higher the saturation temperature will be. So if we look at this TV diagram, they have too many pressure line. The higher the pressure at 5, for example, 8 megapascal, the saturation temperature here is of course higher than 100 degrees C here. Okay, since the pressure is higher than 0.1 megapascal. So if we apply our previous theory to our this TV diagram, then we will have the meaning. The higher the pressure, the higher the saturation temperature will be. So for example, at 22.06 megapascal, where this value is higher than 0.1 megapascal, of course the saturation temperature also higher than 100 degrees C here. So here for 22.06 megapascal, okay, we have critical point. So critical point here means that the state number 2 and state number 3, sorry, state number 2 and state number 4 here is identical. Okay, so they don't have phase changing between state number 2 and state number 4 because state number 2 and state number 4 is on the same point. Okay, so for this case, for 22.06 megapascal, state number 2 and state number 4 is on the same point. Compared to the other pressure, they have their own state number 2, state number 4. This is state number 2, this is state number 4. Number 3 is in between. Okay, for 1 megapascal, state number 2 is here, dekat bucu sini, and state number 4 di bucu sini. For 0.1 megapascal, the state number 2 is in this corner, and state number 4 on this corner. And for 0.01 megapascal, this is state number 4, saturated vapor, and here is state number 2, saturated liquid. So for 22.06 megapascal, please remember the saturated liquid and saturated vapor is located on the same point. So meaning that they are same. Okay, and the temperature here, and the temperature for this point is called critical temperature, and the value is 373.95. Okay, and if we draw a vertical line to B axis, get specific volume, and the value is 0.003106. and this value is called critical specific volume. Okay. PV diagram of constant pressure phase change process of a pure substance at various pressure. And this is the name of this TB, this type of TB diagram. So we have various type of various pressures. Okay. Critical point, as I said just now, the point at which the saturated liquid and saturated vapor states are identical. Okay. This saturated vapor and saturated liquid, this corner, both corners are on the same point for 22.06 megapascal only, not 25 megapascal. So for here, it is not considered as critical point until 22.06 megapascal only for water. Okay, next, the temperature, pressure, and specific volume of a substance at the critical point just now. Okay, critical point just now are called critical temperature (TCR), critical pressure (PCR), and critical specific volume (VCR). And the value are 22.06 megapascal for the pressure, 373.95 degrees C for the critical temperature, and 0.00310 for the critical specific volume. Next, okay, we still in PV diagram with various pressure, as we discussed in the previous two slides. We have 0.01 megapascal, 0.1 megapascal, 1 pascal until 22.09 megapascal. Okay. We have also saturated liquid corner, and also saturated vapor. So this is all of this corner is saturated vapor, and on this side, this corner is saturated liquid state for each pressure. Okay. Now, if we connect all of these points, this saturated liquid point of each pressure, we connect all. If we draw a line connected all of the saturated liquid corner of each pressure, then we will get this black line. Okay. If we connect all of these saturated liquid state of each pressure, we will get this black line. And then if we connect all of the saturated vapor state of each pressure, then we will get another black line, this black curved line. Okay, so now we have moved to another level of understanding of PV diagram. For this, we have a single pressure constant line. After that, we have various pressure line, and now we have curved line that are connecting all of the saturated liquid and saturated vapor state of each pressure line. Okay, so now we are on the next level of understanding our PV diagram. Okay, so on this side, on this left side, okay, on this left curve, the first curve line, this is what we call as compressed liquid region. Any position, any point located on this region, okay, for example here, or even here, as long as on the left side of this curve line, the name of the phase is compressed liquid. Okay, so please remember that in between this curve line, okay, in between these two curved lines, this region is two-phase region or saturated liquid vapor mixture region. So any point located on this region, okay, for example here or here or even here or even here, the name of the phase is saturated liquid vapor mixture phase. And then number 3, this region, which is located on the right side of this curve line, is superheated gas region. So meaning that any point located on this region, for example here or even here, as long as on the right side of this curve line, the name of the phase is superheated gas phase. Okay, so please remember that. This is important for us to know, to understand on how to read our TV diagram or on how to analyze our TV diagram. Okay, if you have any question, please ask me. Okay. Next, still in TV diagram. Okay. Now, as we discussed just now, if you connect all of the point, then we will get this curve line. Okay, the first curve line on this left side is saturated liquid line. On the other hand, on the right side, this curve is called saturated vapor line. Okay, at the beginning of this discussion, we consider only one pressure, right? For example, 180 M, single pressure constant line. Okay, but now on this level, we have various, we can draw various pressure line. Okay, for example, now we have P2 line, okay, which is the value of P2 is higher than P1. The higher the line, the higher the pressure. Okay, if you draw here, meaning that the value of this pressure is higher compared to P2. If we draw a pressure constant line around here, that means the value of this pressure is lower than 1. Okay, now, as we discussed just now, this region is compressed liquid region. So any point located on this region, okay, for example here or here or even here, name of the phase is compressed liquid phase. Second region is in between the curved lines. And this region is saturated liquid vapor region. Meaning that any point located on this region, as long as on this region, okay, for example here or even here or even here or near to this curved line, the name of the phase is saturated liquid vapor mixture phase. Region number 3 is here. This is superheated vapor region. So meaning that any point located on this region, the name phase is superheated vapor phase. At the top of the curved line is critical point. Okay, this is the critical point. So for the water, the value of critical temperature here, if you draw a straight line to P axis, this is 373. And then if we draw a straight vertical line to P axis, this is the critical specific volume. Okay, and then on this TV diagram, we can read another one. So at this point, along this line, along this curved line, along this saturated liquid line, any point located on this saturated liquid line, okay, the name of the phase is saturated liquid. Okay, for example, here, or even here, or even here, the phase name is saturated liquid. On the other hand, any point located on this saturated vapor line, for example, here, or even here, or even here, the phase name is saturated vapor. Okay, this is the important thing that you have to understand. This is how we read our TV diagram. Okay, so please remember that we are going to use TV diagram throughout our semester. Okay, so I hope you can understand very well on how to read this TV diagram. So basically, this is the point, okay, that we discussed just now: saturated liquid line, saturated vapor line, then compressed liquid region, superheated vapor region, and then last one, saturated liquid vapor mixture region. Okay, next we will move to the next diagram. Any questions so far before look at PV diagram? Thank you for your response. Next, we look at the second diagram, pressure versus specific volume, or PV diagram. Okay, basically, PV diagram, the way we understand and the way how we read this PV diagram is actually same as what we have done in PV diagram. The only thing that are different between PV diagram and PV diagram is first this one. Okay, for PV diagram, we keep the temperature constant. For example, in this case, the temperature is kept constant at 150 degrees C. Okay, compared to PV diagram, we kept the pressure constant. We let the temperature change during the phase changing process. For PV diagram, as I said, we keep the temperature constant at 150 degrees C, for example, and we let the pressure change during the phase changing process. So the pressure is changing. So we move this load one by one, okay, in order to make the boiling process occur. It is given, it's still given, but the temperature is keep constant at 150 degrees C. Okay, and then the process will change from state number 1, move to state number 2, state number 3, number 4, until number 5. Okay. The second thing that is different between PV and TV diagram is this line. Okay, we have this kind of line. This is what we call as temperature constant line. Okay, the rest are same as PV diagram. Okay, back to our PV diagram. This is PV diagram. Okay, this is the previous diagram that we discussed. This is P versus V diagram, right? This is our curve line, and we have this dotted line referring to pressure constant line, because we keep the pressure at a constant value and we let the temperature change during the process. Okay, so now our diagrams look like this: P versus V, and this dotted line, we still have curve line where this part is saturated liquid line, still same as PV diagram, and this curve line, another curve line is saturated vapor line, still same with PV diagram. The difference is this one, the dotted line. Okay, the dotted line now look like this, and this is temperature constant line. We keep the temperature constant and we let the pressure change during the process. Okay, here it is compressed liquid region. So any point located on this region is named compressed liquid phase. So any point located on this first curve line named as saturated liquid phase. On this region, this is saturated liquid vapor region. So any point located on this region, the phase name is saturated liquid vapor mixture phase. Okay, next, this curve line, this is saturated vapor line. So any point located on this line, the name phase is saturated vapor phase. The last thing, this is superheated vapor region. Okay, so any point located on this region, the name, the phase name is superheated vapor phase. Okay, and then they have various temperature constant line. The higher the temperature, the higher the line of this temperature, the higher the value of this temperature. For example, T2, this line is upper than T1, right? Higher than T1. So the value of T2 must be higher than T1. If we draw a T constant line as here, so this value, the value of this temperature is lower than T1. Okay, this is a PV diagram. Okay, if we combine all of these three properties, P, T, and V, on the same diagram, okay, then we will get this 3D diagram. But we are not going to focus on this. Just I just give a brief explanation on this P diagram, the 3D diagram. Combine all. Okay, just now we have done that PV diagram, and then TV diagram. Okay, so this is how the phase looks like. Okay, so this region is solid. So on this part, this is solid liquid part. Here, this is solid vapor part and liquid vapor part, and this is critical point. Okay. Contract on freezing, and this one during expanding on freezing. The PVT diagram presents a great deal of information at once. So we combine all properties in one diagram, and we can get the phase name based on this 3D, based on the three properties. But in the thermodynamic analysis, it is more convenient to work with two-dimensional, the PV or TV diagram, not this one. Okay, so therefore I'm not going to focus more on this PVT diagram. Okay, next we will look at property table. So we have done for the diagrams a PV diagram and TV diagram. So I hope you now can understand and know how to read the diagrams. For this slide, we will look at the property tables. So basically, in thermodynamics, we use both diagram and property table. From the diagram, we will look at the table to get the value of each property. So that's why I said this now. Please focus the explanation on the diagram because we are going to use the diagram. If you can't understand or if you don't know how to read the diagrams, then you will face a difficulty later on. Later on means that now, property table. If you can't read the table, then you can't understand the property table. So I hope for those who still confused on how to read the property, the diagrams, PV and TV diagrams, please ask me during our lecture. If not, after this session, you can ask your friends. Okay, let's look at the next level, property tables. The thermodynamic properties are too complex to be expressed by simple equations. Thermodynamic properties here means that pressure, temperature, specific volume, specific internal energy, specific enthalpy, specific entropy. So therefore, properties are frequently presented in the form of tables. So once we have a tables, they have a value of each properties. So from the value, then we can solve many complex problem thermodynamics. So some thermodynamic properties can be measured easily. For example, temperature or pressure. Temperature, we can use a thermometer, and then pressure, we can use manometer or barometer as what we learned in chapter number 1. But others cannot and are calculated by using the relation between them and measurable properties. Okay, basically in property tables, they have these 2, 4, 6 properties: pressure, temperature, specific volume, specific internal energy, specific enthalpy, and specific entropy. Okay, the first two you are commonly see this property, pressure and temperature. The rest, specific volume, just learn in thermodynamics in the last chapter, chapter number 1. Yeah, we have seen specific volume, specific internal energy, and then next to enthalpy and entropy. This is quite new for you. Enthalpy here is a combination of U and PV. We are going to learn in the next chapter, as well as entropy. We will define the meaning of entropy in chapter number 7 at the end of our course. Okay, so basically these are the properties inside the tables. Okay, actually, in order to learn these property tables, I'm suggesting to you to have a set of property tables. And these property tables you can download from my Udemy. Okay. Please print out one set of each student. So throughout this our discussion, start from this week until the end of this course, as well as during your final examination, you will use this table. Okay. So I hope after this, please print out one set of the booklet that I uploaded in my Udemy for uh, for your use. Okay, so we will use the booklet throughout this course. So from the booklet, if you have a booklet on your in front of you, so it's very easy for you to understand the explanation from me. Okay, so please get the property tables, the booklet in the ULearn after this. Okay, for the time being, it's okay. If you have on your hand right now, you can refer to the table, to the booklet. But if not, if you don't have, don't worry. Just look at my my slide. Then after this, please print out. Okay. Now let's look at the first one, enthalpy. We just look at the definition of some of the properties before we move to the tables. Okay, first enthalpy, it is a combination property, a combination of internal energy and PV. Okay, we have two equations here. The first equation is specific enthalpy. Specific means any property divided by mass. Okay, if we divide any property by mass, then we get the name of the property becomes specific. For example, here, enthalpy, if we divide by mass, then the name of this enthalpy becomes specific enthalpy. And the unit, the symbol of the unit is lowercase of h, small h, equal to small u plus p v. U is specific internal energy, P is pressure, and small v is specific volume. So for enthalpy itself, it is uppercase H plus uppercase U plus equal to uppercase U plus PV volume. Okay. So we have this is some a brief definition of enthalpy. Okay. So here we have open system. We have one inlet and one outlet. So as we learn in chapter number 1, for the open system, mass can be transferred in and out as well as energy, right? So since mass can be transferred in and out, so mass itself brings their own internal energy. Okay, so mass itself brings any mass has their own internal energy. So since mass is entering and leaving the system, so mass brings internal energy 1 at the inlet. And then this is PV, means that in order to make the mass entering the system, they must have a force. Okay? They must have a force to push the mass move or entering the system, as well as leaving the system. It must have a force to make the mass leave the system. So that's why once we have force, we can get the pressure. Okay, V here is specific volume of the mass that are entering the system. Okay, if we times pressure with specific volume, it will give us an amount of energy. Okay. So for entering or leaving the system, for example, now we focus on entering the system. The first energy is internal energy of the mass. Second energy is the energy that we get from the P and V. So now we have two energies. If we combine both energies, then we will get the enthalpy, H. Okay. This is how the enthalpy comes from for the case of entering the system. For the case of leaving the system, of course, as I said just now, any mass will bring its own internal energy. So in the case of leaving the system, U2 is the internal energy of the mass at the exit during the leaving. And then in order to make the mass leave the system, they must have a force. Okay? So once we have force, then we can get pressure. Specific volume is of course the volume, the specific volume of the mass itself. So P times V, we get energy. So both energies, internal energy and these PV energies, if we combine them, then we get the enthalpy at the exit. So the exit. Okay, the combination of U plus PV is frequently encountered in the analysis of control volume, this open system. Okay, as I said just now, P times V has energy units. The product of pressure and volume has energy units. Okay, this is how the enthalpy comes from. If you are asking the meaning of the enthalpy, then you can give the definition based on this explanation on the explanation on this slide. Okay, next. Okay, now we will look at the table. Okay, we have another 20 minutes, so I hope we can. Let me check first how many slides. Okay, it's okay, never mind. Let's continue. Okay. Basically, they have three tables. Three tables for the water. The first table is table A4. Second is table A5, and number 3 is table A6. But now we will look at the first two tables, table A4 and table A5. Table A4 is the saturation properties of water under temperature. This is the title of the table. So as I said just now, for water, for a pure substance of water, they have three tables. First is A4, then second is A5, third is A6. A4, the name is saturation properties of water under temperature, and A5 is saturation properties of water under pressure. So in this slide, they have a figure of table A4 only, but table A5 I will explain later on. If you have your own set of property tables, then I can explain later. Okay, but now for the time being, let's look at table A4 only. Okay, for table A4 here, they have a set of properties, basically 6 properties. But for this case, we just only have 3 because I already cut I already cut this figure to a small part. It's okay, never mind. Here, the first one is temperature. On the first column, of this table is temperature. Second is saturation pressure, P sat. And then next is specific volume column. And then second column here is specific internal energy, and then after continue with enthalpy and entropy. But for this case, I just show to you specific volume. For this specific volume, they have two types of specific volume. The first is saturated liquid. Specific volume for saturated liquid, and the unit is VF. Second is specific volume for saturated vapor. The unit is VG. F and G here means that fluid and gas respectively. F refer to fluid or a liquid, and G is referring to gas. Sat here means saturation. Okay, you already learned this. So again, this is specific temperature, okay, or temperature, you can say temperature. Second column is corresponding saturation pressure. Next is specific volume of saturated liquid, then specific volume of saturated vapor. We have another column here, but as I say, I just attach a small part of a partial list of the table A4. Okay, next, VF, as I said just now, this is specific volume of saturated liquid, and VG is specific volume of saturated vapor. Okay. Then we can get VFG. VFG here means the difference between VG and VF. So please remember this equation. So in order to get VFG, you have to find the difference between UG and UF. Okay, VFG, sorry, not UG, VG and VF. Sorry. Okay, VFG equal to VG minus VF. Okay. And then in the same table, table A4, in the column of enthalpy, okay, in the column of enthalpy, they have HFG. Okay, but now my slide here don't have the complete table, so I just explain to you. The HFG or enthalpy of vaporization is the amount of energy needed to vaporize a unit mass of saturated liquid at a given temperature or pressure. Just remember the definition of HFG. In order to get this value, HFG, the equation still same as VFG. You have to find the difference between Hg minus Hf. Okay, HFG equal to Hg minus Hf. Okay, next example 1. Oh, okay, before I forget this one. Okay, we use table A4 and table A5 basically to find the properties for saturated liquid and saturated vapor state. But we can still find the properties for other phases, compressed liquid, what else, saturated mixture, as well as superheated vapor. But for the time being, this table A4 is used to find the properties for saturated liquid and saturated vapor states. Okay, let's look at example number one. Example number one, a rigid tank contains 50 kilogram of saturated liquid water at 90 degrees C. Determine the pressure in the tank and the volume of the tank. Okay, now once you have a question or any problem, please remember that you have to solve the problem step by step. Step by step. Okay, I will share with you the steps, but this explanation is not written in any slide. So you have to write down this explanation. So please get any paper with pen, then write down the step that I'm going to explain now. Okay, first, once you have a question or problem, the first step that you need to do is list down all the value of the information given from the question. List down all the value of the properties given in the question. This is the first step. Second step, draw the PV or TV diagram. Step number 3, transfer the value of the property given into the diagram. Step number 4, come up with the equations that you have learned and solve the problem. Slash refer to table. Okay, so basically they have 4 steps in order to solve any problem in thermodynamics. The first one, as I said, list down all the value of the properties given in the question. Number 2, draw PV diagram or TV diagram. Number 3, transfer the value given into the diagram. Number 4, come up with the equations to solve the problem slash refer table. Slash mean or refer table. Okay, so once we have the problem as example number 1, so we do step by step. Okay, so rigid tank contains 50 kilogram of saturated liquid water at 90 degrees C. Determine the pressure in the tank and the volume of the tank. So for the first step, list down all the information given and the value of the properties. List down all the information and the value of the properties given. So now we have a rigid tank contains 50 kilogram of saturated liquid water at 90 degrees C. So they have a lot of information in one sentence here. Mass, first one is mass 50 kilogram. So write down M equal to 50 kilogram. Phase 1 is saturated liquid water. Okay, write down phase 1 equal saturated liquid water, temperature 1, 90 degrees C. Okay, so basically this is the information given in sentence number 1. Okay, and the other thing is they have another point here. Rigid tank. Rigid tank means that the tank is fixed, no inlet and no outlet. Meaning that, in other words, the volume is constant. Once the volume is constant, V1 equal to V2. Please write down that. V1 equal to V2. Rigid tank is basically V1 equal to V2. So later on, if you find the term of rigid tank, so in your mind, you know that volume 1 or initial volume equal to final volume. Then move to the second question. Determine the pressure in, now move to the second sentence. Determine the pressure in the tank and the volume of the tank. So next, right? P equal to question mark and V equal to question mark. These two properties need to be determined. Okay, so we have done for step number 1. Step number 2, draw TV or PV diagram. Draw the diagram. So draw the diagram is that we have to choose either to draw TV or PV diagram. Okay, so we have two diagrams. So which one is better to draw? So based on the this is the point, the clue how to choose whether TV or PV diagram. So look at the question. Look at the question. If temperature is given, you draw PV diagram. If temperature is given, draw PV diagram. If pressure is given, draw PV diagram. Okay, this is the clue on how we draw the diagram. We're still in step number 2. Okay. So now temperature is given. So draw PV diagram. It's different as shown in my slide. In my slide, the figure is PV diagram. So never mind. As I said just now, PV and PV diagram, the way we read, the way we understand the diagram are same. So since temperature is given, you draw PV diagram. So draw PV diagram, draw the curve line as well as temperature line. So we have single temperature line, right? 90 degrees C only. So draw the temperature constant line. So the line, the value of the temperature is 90 degrees C. Okay, what else? Step number 3. Transfer the value given into the diagram. So as I said just now, you draw the PV diagram, then put the value 90 degrees C. What else can be written in your diagram? Only temperature, right? Because P versus B diagram, we don't know the pressure, and then we don't know the volume, specific volume. These two properties need to be determined. Okay, that is step number 3. Step number 4, come up with the equation and put to the table, right? Okay, now you have your own diagram right now on your hand in front of you. P versus B diagram. Okay, the rigid tank mass is 50 kilogram. V1 equal to V2. Okay, okay. In your diagram, uh, you can get P saturation, right? P saturation, get the P saturation. Draw a line to P axis line. Draw a line to P axis line from the saturated liquid point. So if you look at your PV diagram, you can determine saturated liquid phase, right? Saturated liquid phase. Determine the point of saturated liquid phase. So from the point, draw a horizontal line to the pressure line. This one. This is saturated liquid phase. So from this point, draw a horizontal line to your PV diagram. So here, this is Tn, but your diagram, this is P, right? P. So this point is P saturation. Saturation. P saturation. Okay, so wait a minute. Let me check first. So temperature is 90 degrees C, saturated liquid vapor. Okay, you are given first phase, which is saturated liquid, right? Saturated liquid water. So determine the phase, the position of this phase, saturated liquid. So now you have the point, right? So the point is here. The point is here. This is saturated liquid. Okay, after that, what shall we do? Okay, very simple. Draw a straight line here from this point. Draw a horizontal line to your P axis line. So now here, this is P saturation. Okay, temperature is 90 degrees C. So if you have your own table right now, look at table A4, or A5. But since temperature is given, okay, look at table A4, because table A4 under temperature, meaning that if temperature is given, you have to look at table A4. If pressure is given, look at table A5. Okay, so now here, this is temperature table, table A4. The given temperature is 90 degrees C, right? So at 90 degrees C, the P saturation is 70.183. So this is the temperature, the pressure at here. Okay, P set, as I said just now, get the P set. So P set is 70.183 kilopascal. So this is the first answer, pressure in the tank. Okay, for the volume, draw a vertical line from saturated liquid phase two V exists here. Okay. So this point is VF. This is VF. Why VF? Because if you look at the meaning of VF here, this is specific volume of saturated liquid. Since the phase is saturated liquid, then if we draw a vertical line, since the phase here is saturated liquid, if you draw a vertical line to V axis, you will get VF. Okay, so VF. So look at the table. Look at the table back. At 90 degrees C, okay, at 90 degrees C, we have obtained P set just now, 70.183. And then move to next column, find VF. So VF is this column. So the value of VF at 90 degrees C is 0.001036. This is the value that we are going to use or to write here. Okay. So VF at 90 degrees C equal to 0.001036 meter cube per kilogram as written here. Okay. So this value is obtained from table A4 just now. Okay, next, the total volume of the tank. This is the property that we need to find. So, as I said, in step number 4, use the relevant equations / refer table, right? So now we are in step number 4. So the relevant equation is V, uppercase V equal to MV. Okay, please remember this one. M is volume, small v is specific volume. Okay, the unit of volume is kilogram and the unit of specific volume is meter cube per kilogram. So the byproduct between M and small v is meter cube. So that's why 50 kilogram, the mass of the pure substance, times the specific volume of this phase, saturated liquid water phase. So final answer is 0.0518 meter cube. Okay, this is how we solve the problem based on step 1 until step number 4. Okay, this is the simple one, the simplest example. So I think enough for today. We will continue our next discussion on chapter number 2 next week. So next week, please bring your own set of table, a set of booklet. We will use the booklet to solve, to learn chapter number 2 as well as to solve example related with chapter number 2. Okay, so I think that's all for today. Continue next week. So thank you for your attention. See you on next week. Okay, before we end our session, today, I just want to re-inform with you. We will start a lab session next week on Tuesday for section number 2 and section number 3. and Thursday for section number 4. So ketua kumpulan sila pastikan ahli kumpulan yang akan hadir, maksimum 3 orang pelajar untuk sesi lab pertama. Okey, sebelum kamu hadir ke lab, pastikan kamu telah membawa lab sheet masing-masing. Kita ada 3 eksperimen, pastikan kamu bawa ketiga-tiga lab sheet tersebut. Lab sheet eksperimen 1, lab sheet eksperimen 2 dan lab sheet eksperimen 3. Dapatkan daripada unit dan bawa pada hari Selasa dan juga hari Khamis mengikut section masing-masing. Okey, disebabkan isu semasa sekarang, walaupun rentas negeri telah dibenarkan, tetapi berita semalam menunjukkan kadar kemasukan ke hospital kembali meningkat. Okay. Dan itu yang pertama. Yang kedua, Melaka akan mengadakan pilihan raya. So, saya berdasarkan kepada kedua keadaan semasa ini, saya khawatir kes jangkitan akan meningkat. Okay. So, berdasarkan kepada dua perkara ini, saya mengharapkan minggu hadapan kamu dapat mengambil ketiga-tiga data untuk 3 eksperimen dalam masa 3 jam. Okay. So, kalau boleh kita habiskan sesi face to face pada minggu hadapan. 1 kali saja perjumpaan. Sebabnya saya khawatir dengan keadaan semasa, kes kemasukan ke hospital kembali meningkat berdasarkan laporan KKM semalam, dan juga Melaka akan mengadakan pilihan raya. So ramai terkhuatir keadaan seperti di Sabah berulang, pilihan raya di Sabah berulang. So that's why dengan dua perkara tersebut, seperti yang saya beritahu, kita akan adakan sesi lab 1 kali saja. Okay, 1 kali saja. So ketua kumpulan pastikan 3 orang pelajar yang terlibat minggu hadapan hadir dan membawa sekali ketiga-tiga lab sheet untuk 3 eksperimen yang akan kamu ambil datanya minggu hadapan. Okay, so ini tanggungjawab ketua. Sekiranya ada ketua kumpulan kamu yang tidak hadir, anak-anak buah pastikan beritahu ketua kumpulan. Sekiranya ada kumpulan yang tidak mendapat info yang saya beritahu hari ini dan mereka tidak membawa apa yang saya suruh, so kebaran kalian untuk kamu dapat kosong bagi sesi lab tinggi. Okay, so ahli kumpulan pun bertanggungjawab sampaikan perkara yang saya beritahu ini kepada ketua kumpulan dan juga rakan-rakan di dalam kumpulan kamu. Okey, so itu saja daripada saya hari ini. Terima kasih semua. Kita jumpa insya-Allah hari Selasa dan Khamis. Dan juga Jumaat. Okey, terima kasih semua. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Doctor.
Thank you, Doctor.